This video is on the physical chemistry experiment, the enthalpy of sublimation and the lattice energy of solid argon. The video will cover the theory, the calculations, and the experimental procedure. I'll begin by showing some slides. So in the experiment, this first slide shows schematically what's happening. So in the experiment, you'll have a solid block of copper that has two chambers in it, one for argon and one for nitrogen. And you'll begin by filling these with gases. The two chambers do not communicate with each other. And you'll cool it to a very low temperature, and then you'll take your measurements over a variety of temperatures. Now, the nitrogen serves really as a thermometer. So the temperature is known as a function of the vapor pressure of nitrogen above liquid nitrogen. So you'll be able to measure the temperature that way. Then we'll measure the argon pressure also, and from those two sets of data, we'll be able to determine the enthalpy of sublimation. Now, both of the chambers will be connected to open tube manometers for measuring the pressure. Now, what you will do to achieve the low temperature, as you'll see, is submerge the system in a dewar filled with liquid nitrogen. And then we'll actually partially evaporate the liquid nitrogen. That will cool us yet further. So we'll go below the boiling point of liquid nitrogen at atmospheric pressure, which is 77 Kelvin. So what data will you need to take? First, you'll have to take the barometric pressure because it's an open-ended manometer, open tube manometer. Then you'll measure the heights in both manometers on the right and the left. They'll be filled with mercury, so you should take between 6 and 10 data points, different temperatures. You'll get these sets of left and right millimeters of mercury, which you can combine to get pressures, and then from pressures, you'll be able to determine temperature and vapor pressure. How's that done? Well, from the nitrogen data, you'll get the pressure first, and then with an equation in the manual, from the pressure, you'll determine the temperature. Remember, that's a vapor pressure of the vapor above the liquid nitrogen. Then for the argon, you'll simply combine the two heights and get the vapor pressure, including, of course, barometric pressure. So you get all those data. What do you do with those data? Well, you are really going to apply the Clausius-Clapeyron equation. That applies to any condensed phase gas phase equilibrium. You thought of liquid gas before, but it also applies to solid gas. That's the situation. So you'll plot the log of the pressure versus 1 over temperature. And you'll probably get even better line than you see here, or less scattered data. You'll fit that then to a line, okay? And you'll do a linear least squares fit. You'll do a regression because you want an uncertainty in the slope as well as the slope. In any case, from the slope, you'll be able to determine the enthalpy of sublimation via this equation. This should be familiar from earlier experiments. And then from this, you can simply multiply the slope by minus r, and you'll have the enthalpy of sublimation of solid argon. So that's pretty cool, I think. And that is your initial, that's the first thing you need to determine, and you can compare that with literature data, see how accurate you were. We want you to go one step further, though, and determine something called the lattice enthalpy of the solid argon based on your enthalpy of sublimation. So I'm going to talk about that a little bit. So here you've got a sort of cartoon of a crystal lattice of crystalline solid argon. The crystal structure is actually face-centered cubic. You can look that up, see what it looks like. When the substance sublimes, of course, you end up with gaseous argon, and the molecules move apart from each other. In the crystal lattice, the interactions between the argon atoms are quite favorable. And so those favorable interactions are broken when you form the gas. To do that requires an input of energy or enthalpy. So let's talk about how you determine the lattice enthalpy from your enthalpy of sublimation. Here's the equation. It's in the lab manual. The lattice enthalpy is really the enthalpy of the lattice with all the atoms are still. They're at rest. If they were truly initially at rest in the experiment, then the lattice enthalpy would be equal to the sublimation enthalpy. However, we know from quantum mechanics that the atoms will never be at rest. At the very least, there will be a vibrational 0-point energy. And so that has to be accounted for. So that's what this second term is about. This capital theta D is a constant that's been tabulated for argon. It's called the characteristic temperature, also called the vibrational temperature. It's not really a temperature. It's simply a constant that has units of Kelvin. That's why we say temperature, but it's really just a constant. Happens to be 93 Kelvin for argon. So you can combine that with your enthalpy of sublimation and you'll have your lattice enthalpy. Okay. We want to compare that with a theoretical model. So let's talk about the model. Okay. So the lattice enthalpy from theory then. Now we will be combining theory with some data, but it'll be different data, not your data. The theory is this. So think about these argon atoms and think about the energy that for a pair of them as a function of how far apart they are. We know that if they get very close, there's a repulsive wall. As they get a little farther apart, there's an attractive well. And then if you pull them yet farther apart, the energy essentially becomes, there's no interaction, it becomes zero at infinite distance or very large distance. So scientists have played with functional forms that will describe this curve quite well, not perfectly, but quite well, for a variety of substances. Then they derive parameters for each substance. And the potential, the form of the potential is very famous, called the Leonard-Jones potential. So the first, notice it's 4 epsilon times this difference in parentheses. So let's think about what the various parts mean. The first part is to the 12th power and it's positive. That basically is describing the repulsive wall. Sigma is a parameter and you divide sigma by r and then we'll take that to the 12th. Okay, if r is small, that's a very large number. When r gets larger, this whole term gets smaller pretty quickly. On the right-hand side, we have a negative term that's raised to the 6th power. So it's favorable. And that's really how we get the bottom of the well here. When you take the difference of these two terms right here, you'll be positive at very small r, but eventually be negative. And as r gets very large, of course, you go to 0. Also notice when sigma happens to be equal to r, you'll get 1 minus 1, which is 0. So the potential energy is 0 when r is equal to sigma. Okay. So this is a Leonard-Jones potential. And if you have epsilon and sigma parameterized for your particular substance, then you'll have the curve. Well, argon has been parameterized with a Leonard-Jones potential. And so from that, we can derive a theoretical value for the lattice energy. It's theoretical because it's based on this model equation, but we use experimental data from various sources, including things like the non-ideality of gases that can be measured. In any case, you've got epsilon, this is times Avogadro's number divided by the gas constant is equal to this, and then sigma and d. Now d is the nearest neighbor distance for for solid argon, which happens to be, as I said, the crystal form is called face-centered cubic. So this ignores some things. It only takes into account the shortest distances, the nearest neighbors, not the others. But they will be the most important because of these large powers here. So you actually just plug the numbers you're given in to get this theoretical value of the lattice enthalpy, and you can compare it with your experimental. Okay. So those are the things that you need to do with your data. So next, let's talk about the experiment itself. Before we actually show the video of the experiment, I wanted to show you a schematic because the apparatus is pretty complicated, and therefore I want to show you this experimental schematic. So take a look here. You've got your argon and nitrogen gases on either side. You've got a vacuum pump down at the bottom. Right here in the middle, upper middle, are the chambers. They're connected to this cap. And of course, you can put gas into either chamber. Now we've got nitrogen on the left, by the way. And then we have a dewar, which will be filled with liquid nitrogen, and we can raise and lower the dewar on this jack. Okay. You'll also see the open-ended manometers. So I have one end of each is open. You'll find in the laboratory it's connected to a trap, and in case mercury should escape. We hope it doesn't, but the trap itself is open to the air. So effectively, the manometer is open to the air. Now, this complicated apparatus allows us to do a number of things. We can evacuate the whole system. We can then add the gases to either side, isolated, the nitrogen and the argon side. So that's what all of this does. The red circle, the red diagrams here are three-way stopcocks, and the blue ones are two-way stopcocks. So you will want to study this to see just how it is. How do you have to turn these stopcocks in order to first open the system to the vacuum so you can evacuate? Then you want to think about how you turn these stopcocks so that you can isolate the argon side and introduce argon only to that side. And then same thing for nitrogen. Okay, I won't walk you through it, but you'll want to study it. Okay. So let's assume, so now we're ready to do the experiment, let's say. The first thing we'll do is purge the system. That means we evacuate all the gas out because there may be some air in there or something. You want to begin with nothing. And then you'll fill sequentially first the argon side with argon, then the nitrogen side with nitrogen. And once you fill them up, the argon chamber will be in contact with the manometer always. And the nitrogen chamber will be in contact with the nitrogen manometer always. So you'll always know the pressures inside the chambers. Okay. So we've now purged the system. We filled with gases, but the system's at room temperature. Next thing you'll do is raise that dewar that's filled with liquid nitrogen and by turning the jack. And of course, the whole system is going to get much colder. It'll go down to 77 Kelvin. Once you've done that, we need to get colder. And so you were going to add more liquid nitrogen. At this point, you'll be adding it through the spout up here. And I should have said, before you do add that liquid nitrogen, you will have to form a seal between the dewar and the cap. And you'll be shown in the video of the actual experiment being done how you create that seal. We have some rubber that will seal those two. So then you'll add liquid nitrogen as much as you can without spilling it. So you will add insert the stopper, and then you will evacuate to the lowest temperature. In order to evacuate, you will have to turn this particular stopcock so that you evacuate this whole dewar cap system. Of course, you will not be evacuating the chambers, only the dewar cap system. As you evacuate, the temperature will drop. Okay. Once the temperature is dropped as low as you can get, which will be you won't know initially. There's no pressures, so you'll be given some guidance. You'll be get it down to about 65 Kelvin. Then that's as cold as you'll get. You'll remove the stopper, and you'll start taking your measurements. After you take your first measurement, you will then heat the whole system in increments. And the way we'll be heating is putting a metal rod that you've heated with hot water into the liquid nitrogen through here, and that will gradually heat the system. Then you'll take both pressure measurements, nitrogen and argon, and that will tell you the temperature and the pressure of the argon. You need 6 to 10 measurements. And then when that's finished, you are done. The last thing I want to caution you is when you disassemble the apparatus, you must be very, very careful. Why? If you lower that dewar, the chamber is going to rapidly get warmer, and any solid argon and liquid nitrogen will pretty rapidly sublime or evaporate. If your system is still closed, the pressure could force the mercury out of the manometer into the trap. And I've seen it happen with such force that you sometimes have mercury even leave the trap, and it has to be cleaned up, and mercury can be dangerous. So you want to be very careful, and you should really get your instructor close by when you do that. So this concludes the introductory portion of the video, and now we'll proceed with showing you the experiment itself.